Blood pressure, hopefully you know, is a measurement of pressure that the blood exerts against the arterial walls during various stages of heart activity. The most probably important thing to know about blood pressure is it is an indication of tissue perfusion. So blood pressure equals perfusion through activity and at rest. And as we're going to learn here shortly, blood pressure is actually regulated by several different systems of the body, including the heart, the kidneys, and our peripheral vascular system. Okay, this is just another review slide, but what I want you to zero in on here is what systolic and diastolic pressure really means. Systolic pressure is when the heart is contracting, so it's the working phase. It's the pressure that the heart has to overcome in the vascular system to pump out blood. And then the diastolic pressure is the resting phase. So the heart's at rest, and that's just like the standing pressure in the whole body. And hopefully that will make more sense here, because when that resting, that's why we worry about that lower number. When that lower number is higher, that's a higher pressure that the heart has to overcome for the next contraction. And so that makes the heart work harder. And in the long run, that's not good for the heart. Representation of the things that affect or create your blood pressure. Because when we get into talking about cardiac blood pressure medications, you're going to see where all of those medications plug into. Because that's the thing with blood pressure. It's actually regulated by several different systems, as I said, and it's pretty complicated, and therefore that's why we have so many different blood pressure medications, because there isn't just one pill that can do it all. And that's why people end up usually on multiple blood pressure medications, because it is such a complicated system to be regulated. Okay, so we're going to start here with this diagram at the very top with cardiac output and systemic vascular resistance. Those are the two major components that affect blood pressure, and then we're going to break down and look at what constitutes cardiac output and what constitutes systemic vascular resistance. Okay, let's talk about cardiac output. This is a formula that you do want to have memorized, if not already. And basically it's saying cardiac output equals heart rate times stroke volume. Heart rate is related to how well the heart is beating, also how fast, so the contractility, how fast, how slow. And then stroke volume is related to your blood volume, and it's how much blood is pumped out with each heartbeat or each stroke. And it is based, whether it's high or low, based on how much blood volume you have. Okay, so let's talk about what affects myocardial contractility, i.e. the heart rate. And first and foremost, there are receptors called cardiac beta 1 receptors. And hopefully that beta sounds familiar, because you, in your lower respiratory lecture, you learned about beta 2 blockers or beta 2 receptors that are in the lungs, and then you take medications that are blockers, beta 2 blockers. So it's the same concept. Hopefully some bells and whistles are going off already, and you're like, oh, beta blockers. So yes, we have receptors located in our heart, and they're like neuroreceptors. They are affected by, right below it, you'll see that the sympathetic nervous system, the fight or flight system, epinephrine. So when you are stressed, when you're anxious, when you are afraid, when you are exercising, when you have a fever, all of these things call for an increased heart rate. The brain, the nervous system recognizes that, puts out epinephrine, activates these beta 1 receptors that increases the myocardial contractility, which basically means you're increasing the heart rate. So we'll learn here in class that when we take our beta blockers, they block this sympathetic response, blocking the epinephrine, and therefore basically relaxing the heart, lessening the workload on the heart, and also as a side effect, decreasing the heart rate. Okay, and right next to that, we're going to talk about stroke volume, or what affects the blood volume, therefore how much blood the heart can pump out with each beat. And hopefully right off the bat you see renin, angiotensin, aldosterone system. So that again should make bells and whistles go off and go, oh, that's the kidneys. Yes. So the kidneys are the direct player in affecting our blood volume. And mostly it is through the RAA system. And hopefully you guys know at this point that when the RAA system is activated, the end product is the ADH, or antidiuretic hormone, also called vasopressin. And that's another word, vasopressin, that you're going to want to stick back into your memory somewhere, because next semester when you talk about shock, you'll learn that vasopressin is something that we can give to elevate the heart rate, elevate the blood pressure, increase the blood volume, and help in a shock situation. Also, hopefully, again, for next semester, tuck it away in your brain, but we have, again, some chemical reactions going on in the heart and in the kidneys that affect blood volume, and they're called atrial natriuretic peptide, ANP, but what's more important is the brain natriuretic peptide, BNP, and you're going to learn with congestive heart failure that you can draw a BNP, get a level, and the higher that level is, the more it's telling you that the heart is having a hard time dealing with the stroke volume and therefore is at risk for fluid volume overload, which is the main problem for congestive heart failure. So what's most important here to know is that the kidneys are also directly related to blood pressure regulation, and like I said in class, you're going to see that this is actually where ACEs, angiotensin converting enzyme inhibitor, and our ARBs, angiotensin 2 receptor blocker, again a blocker, we're going to be blocking this RAA system, and therefore through manipulating blood volume and also relaxing peripheral vascular resistance, that we can regulate blood pressure. Okay, let's go up to the other side of the of this graphic organizer and talk about systemic vascular resistance. I told you we were going to spend a bit of time on this, but this is really the heart and soul of blood pressure and regulation, why blood pressure has the side effects that it does, hypertension has the side effects that it does, and why we use the different types of medications. So really, in a nutshell, everything right here explains the management of hypertension. So let's first go to the far right and talk about vessel compliance and atherosclerosis. So we learned in upper respiratory system lung compliance, and so the same concept of compliance, or how pliable, how soft, how well does it expand and recoil the blood vessel itself. And the number one thing that can affect how well the blood vessel can expand, and we're talking about the arterial blood vessels, so the arteries, and is atherosclerosis, or plaque buildup. And that basically causes, when that fatty plaque builds up on the inside of the arterial walls, it stiffens the walls and therefore decreases the ability of the arterial blood vessels, which are smooth muscle, to be able to expand, and contract with each pulse or heart rate, stroke volume basically. And so that hopefully in a nutshell also explains why, atherosclerosis, or the plaque and the fatty buildup, is so bad. It starts actually affecting your blood pressure, and then eventually your blood vessels, and then eventually your heart, your brain, and your kidneys, and causes all the chronic health problems that we see. Now on the other side, the vessel diameter, that's basically how, narrow or wide it is. And again, it's smooth muscle. We got to remember the the arteries are actually muscle, where the veins are epithelial tissue. And again, as you can see, it's related to the compliance, which is related to the atherosclerosis. So the atherosclerosis not only hardens or decreases the compliance, it can actually decrease the diameter. And additionally, just as it shows there, adrenal medulla, it also is affected by that fight or flight adrenaline, so adrenal medulla. And again, when we are stressed, we're scared, but we're exercising, smoking, things like that that decrease the diameter of our blood vessel will increase the pressure. It's harder to blow through a little teeny straw when we're going talking back again about the lungs than it is to blow through, a big tube, like a paper towel, roll or something like that. So that is vessel diameter and vessel compliance affect the systemic vascular resistance. Again, systemic vascular resistance is what the heart has to overcome with each systolic contraction, working of the heart. And if there's more pressure out in the periphery, so we're talking about our legs and our arms, the peripheral, systemic means periphery, that will raise that systolic number, that top number. There's more pressure that has to be generated to overcome that resistance. Okay, and lastly, we'll just quickly talk about vascular alpha receptors. Alpha receptors are similar to beta receptors, but they work on the peripheral vascular system, so the systemic vascular resistance. And when they are activated again by the sympathetic nervous system, they create dilation of the blood vessels. And so they can rapidly actually decrease blood pressure or increase blood pressure. If it's activated, it causes constriction. So our blockers, our alpha blocker antihypertensive medications are actually some of the oldest medications that we've had, but also have some of the most significant side effects for hypotension. So you actually don't see people, you don't see them used as much anymore, and you don't see people starting on them new now. If somebody is on an alpha blocker, they've probably been on it for a while, and they've gotten used to that side effect of hypotension. They've been regulated just right, and it's continued to work for them. So we're not going to go in depth and talk about alpha receptors, but you do want to know that those drugs are still out there, the alpha blockers. And the biggest thing to remember about alpha blockers is that they have a significant risk, increased risk for hypotension and orthostatic hypotension, because they block the constriction, the normal constriction that when we go from sitting to standing, we should be constricting our blood vessels a little bit to keep the blood pressure up. But when you block that ability, you are at a risk for like I said, hypotension, orthostatic hypotension, even syncope. So they're just not used that much anymore.